Hello, this is going to be a short video going through a couple of example problems that I did in class. So to start off with here, I've got this problem where we've got a spider and it's hanging from a little piece of web from the ceiling. And the things that we know here, we know that there's an angle of 20 degrees there. So what's happening is the spider is hanging and it's kind of like there's wind blowing. So think of this as like outside on a porch or something like that. And the spider is at rest. It's kind of just sitting there over off to an angle, but it's being blown over to the side by some wind. So, so what we've got here is I'm going to tell you that the mass of the spider is equal to 0.1 grams. All right, and then additionally, I'm going to say that there is a horizontal wind or which we'll call an air resistance force in this case, and we've got to figure out all of the forces occurring on this spider. So I'll go through and kind of talk about the different work that would be involved with this problem. First thing is always to make an FBD, so if you want to pause the video and try and make the FBD on your own, that would be alright, but I'm going to go ahead and just go through it here. So the things we've got, gravity is going to be going down, so we've got Fg going down, and then we've got that wind, that air resistance, blowing it off to the right. The evidence that this force is going right is that the spider's off center, so it would make sense that if the spider's sitting off there to the right, that the air is blowing to the right. So that's where that's coming from. And then we have a tension force. The tension force is always going in the direction of the rope or the string or whatever is attached to it. So if you were looking from the spider's perspective, the tension force is going up this way. All right, so there's a tension force there. Now we can use some of what we know. The gravitational force, if it's a 0.1 gram spider, it's a 0.0001 kilogram spider. Multiply that by 10, and you should be able to get that the gravitational force is 0.001. And that is newtons. Now it takes some thinking here, but what we know is that that's a downward force. The only upward force that exists to oppose that is this upward component of our tension force here. And so what we've got then is that this is also equal to 0.001 newtons. And then you can do some trigonometry on this. We know that this angle here is 20 degrees, and we know that this angle down here is 70 degrees. All right, so if you do some trigonometry on that, you should find that we get sides here of 0.00106 for the hypotenuse there, and for this side that is on the bottom, the horizontal component of this, you should get 0.00036 newtons. All right, doing a little balance here, we should see that if this is the right component of this, if the component of the tension force, or sorry, the left component, the component of the tension force that's going to the left is 0.00036, then this FAR force, which is going to the right, those are the only things happening horizontally, so that should also be 0.00036, all right, newtons. And so just to summarize here, our answers, we have Fg equals 0.001 newtons, and then I'll just write here Ft ends up giving us 0.00106 newtons, just so that that's really clear, and then FAR is equal to 0.00036 newtons. All right, and then we've got our Fg here, which is 0.001. Okay, so that is one of the problems. So this is our second problem here. What we have is we have a ball and it is submerged underwater in a river, and so you can imagine the current of the river is sort of going along here. The current is moving to the right, and there's a ball that's tied by a rope to the bottom of the river, and the current is pushing the ball off to the right, and so it's at a bit of an angle there. I've given you some information. We know the mass of the ball is 2 kilograms. The volume of the ball is 0.01 meters cubed. The density of the water is 1,000 kilograms per meter cubed. And then, as I said, there's this horizontal force coming from the water. In this one, again, we're just going to start by constructing a force diagram. So if you want to go ahead and try and do that on your own, maybe pause the video. The forces acting on this one here, we've got gravity that's going downward. That is Fg. All right, then we have that tension force, which is going up and to the right. All right, which I'll call Ft. All right. This tension force is going down and to the left because, again, it's going to go in the direction relative to the ball, the direction that the rope is pointing. So we're going down here and to the left. So we get Ft. Then the applied force, the force coming from the water that's pushing the ball forward. And then there should be a buoyant force on this one as well. Okay. So what we have to do now is we have to kind of look through and see what we can find. The gravitational force, because we have the mass, is easy. So it's 2 kilograms, which makes this 20 newtons. We can calculate the buoyant force from our buoyant force equation. We know buoyant force equals G times the density of the fluid times the volume. So in this case, we've got 10 times 1,000 times 0.01. If you multiply those together, you get 100. All right, so that tells us our buoyant force is 100. 100 newtons. Now, this confuses some people because they look at the gravitational force and they look at the buoyant force and they say, wait, those are going directly in opposition to one another. Shouldn't they cancel each other out and be the same? No, because there's something else here that's happening in the vertical direction. If you look at this tension force, it's got a horizontal component to it, but it also has a vertical component to it. And so it's interacting along this vertical axis as well. So that means we have to take it into consideration. We know the gravitational force is downward 20. The buoyant force is upward 100. This tension force has to balance everything out. So if we think we have 100 up, but we only have 20 down now, we need another 80 newtons happening in the downward direction. Now this is a 45-45-90 triangle. All right, so if you do the trigonometry on this, you should find that we have 80 newtons along the side here. All right, and then 113 newtons along the tension force here. And then that tells us that we have an applied force here that is equal to 80 newtons as well, because this, in the horizontal direction, all we have is that horizontal component of the tension, which is going left, and the applied force, which is going to the right. So this is balancing out with that, and it's 80 newtons. Okay, so those are all the bits there. The big things here, we've got gravity is equal to 20 newtons, buoyant force is 100 newtons, applied force is 80, and that tension is 113 newtons. For this third problem, what we have is we have a block that's being dragged along by a tension force, and what we know here is that it has a mass of 1 kilogram. The tension force that's pulling there is 15 newtons. And then I ask you for mu, which is the friction coefficient. And so a couple things here indicating that there should be friction. One of them is that I've asked for the friction coefficient. So there's that. But also if we draw the FBD, and again, I'm going to draw the FBD for this situation now. So if you want to draw it yourself, you might want to pause the video. But we have here gravity down. All right, then we've got tension, which is going, in this case, up into the right. Then we've got a normal force, which is going straight up. All right, and then the friction force has to balance it out. There has to be something going to the left here because we have a force that has a rightward component to it. So there's got to be a friction force here to counteract that leftward force. And so in this case, I've given you some information. I told you that the mass was 1, so we know that the gravitational force is 10 newtons. We also know that for this tension force, we've got a right angle here. This is 20 degrees. We know that the tension force is 15 newtons along the hypotenuse. All right, if we go ahead and do the trigonometry on this, you should find 5.1 for this vertical component, and then 14.1 for the horizontal component. Now this is another one of those confusing situations because we've got 3 forces that are happening in the vertical direction. We've got gravity that's going down, we've got this tension force has an upward component to it, and normal has an upward component to it. So both of the upward forces together have to cancel out with the gravity, which is going down. Gravity is 10, we've already got 5.1 newtons up. That means that this tension, or this normal force here has to be 4.9, so that it equals out the forces going up with the forces going down. 4.9 up from the normal, 5.1 up from the tension, that equals 10. Gravity is 10 going down, so we need 4.9 newtons on the normal force. All right, now the friction force, that's going to the left. There's a rightward component to the tension force. Those are the only things happening in the horizontal direction, so that this has to equal 14.1 newtons as well. And then we're supposed to calculate the friction coefficient here, that's mu. We know that Fr equals mu times n. Just plugging the numbers in here, the friction force was 14.1. That equals mu times our normal force, which was 4.9. Divide both sides by 4.9. You get mu equals 2.87. And there are no units on the friction coefficient, so that's good. All right, I have another few short problems that I'm going to present in another video, so if you want some more practice with these, there will be another video coming soon.